In this session, we're going to talk about Gibbs free energy. You can follow along in OpenStax Chemistry section 16.4. Now, this video, as well as the next two, are all going to be about section 16.4. So the purpose of this video is just to define free energy, calculate it using this formula delta G equals delta H minus T delta S, use that to predict spontaneity, and then we'll talk a little bit about the temperature dependence of spontaneity by calculating the crossover temperature. Finally, the example that we're going to do applies to some biochemical systems. So we said before that in any spontaneous process, the entropy of the universe increases. That is the second law of thermodynamics. And so that means that delta S of the universe is going to be greater than 0 for any spontaneous process. We also say that since delta S of the universe is the sum of the systems and the surroundings, that in order for entropy of the universe to increase, that must mean that either the entropy of the surroundings or the system is increasing, or maybe both, and that any decrease in one has to be counterbalanced by an increase in the other. So what's tricky about this is that we include delta S of the surroundings. It turns out that our experimental design is always set up to measure information about the system. It's really hard to measure things about the surroundings because the surroundings are everything. So it would be really helpful if we could figure out how to describe spontaneity using only terms related to the system, because the system is what we can measure in an experiment. So it turns out that delta S of the surroundings is related to delta H of the system. So delta S of the surroundings equals negative delta H of the system divided by T. So let's think about what that means. If you have a system where delta H is negative, that means that this is exothermic. When heat is released by the system into the surroundings, it raises the temperature of the surroundings. And we said before that raising the temperature of the surroundings increases delta S. So an exothermic reaction increases delta S of the surroundings. In the same way, if you had an endothermic reaction, then the surroundings would decrease in temperature as the heat went from the surroundings into the reaction. And so that would mean that delta S of the surroundings decreased. So it turns out that the amount of heat that is released from or absorbed by the system is related to the amount of entropy that is lost or gained by the system, and in proportion to T. And so that's why we have a negative sign in front of delta H of the system. And we know that entropy is dependent on temperature, so that's why the temperature is there too. Okay, so let's go back to that second law of thermodynamics thing. And if we have delta S of the universe, we said equals delta S of the system. And then instead of delta S of the surroundings, we're going to put in delta H of the system divided by T. Okay, now that's fine, but that T there is kind of awkward, and then there's a negative sign in front of delta H that we're going to find is awkward for us later. So we're going to multiply this whole thing by negative T. So negative T times delta S of the system. And so really we're just going to massage this a little bit to make it more convenient for us. Okay, so if we do that, if we kind of distribute what we've got there, we've got negative T times delta S of the universe equals negative T delta S of the system plus delta H of the system, because we cancel the T and we distribute that negative sign. Now, that negative T delta S of the universe, it's really hard to measure things about the universe too. If you thought the surroundings were difficult, then measuring the universe is also really a challenge, because you have to measure both the systems and the surroundings. You can't measure it directly. It's kind of a mess. So let's define delta G as equaling negative T delta S of the universe. So this will be delta G of the system. So we'll substitute that in. Delta G of the system equals, and I'm just going to rearrange to put not to have that negative sign on the front there, delta H of the system minus T times delta S of the system. So now we're going to define this new quantity. Delta G is free energy, and that the free energy is related to the delta H, the enthalpy, and delta S, the entropy of the system. So because of this, we see the sign relationship between negative T delta S and delta G of the system. And so we said that if delta S of the universe were positive, that was spontaneous. But if we put a negative in front of that, we see that a delta G that is negative, less than 0, means a spontaneous process. And so the opposite is true. If delta G is greater than 0, if it's positive, then that means non-spontaneous, or spontaneous in the opposite direction. And then that also means that if delta G equals 0, that's going to be equilibrium, where equilibrium, as you know, means no net change. So we're defining this quantity as free energy. What do we mean by free energy? So here, free in the context of energy means something like available. So kind of like if somebody asks you if you have any plans for the weekend, and you say, no, I don't, I'm free. But remember, you shouldn't be going out, social distancing. But so free here means available to do work. And we call this Gibbs free energy because this idea was first articulated by Josiah Willard Gibbs. And Gibbs was a Yale man, like myself. He went to Yale. He was one of the first engineering PhDs awarded in the United States. Spent his whole life living in New Haven, Connecticut, thinking about important science, math, engineering type things. And was generally known as being kind of a quiet, all-around nice guy. So there you go. You can get to know Gibbs a little bit. So Gibbs free energy is the energy available to do work on the surroundings in terms of the parameters of the system. Okay, so it's the energy that is available. So if the maximum amount of energy that could be released to the surroundings in terms of the parameters of the system. Delta G equals negative H minus T delta S. So we see that spontaneity thus depends on two factors, both enthalpy and entropy. You have to think about how they work together. Kind of like delta H and delta A, and to a lesser extent delta S, the absolute value, like the numerical value of G, doesn't matter. Only changes matter. So those changes are, between the products and the reactants. Delta G, Gibbs free energy, makes assumptions that during the course of the reaction, the temperature is constant and the pressure is constant. There are other types of free energy that if you become a chemistry or physics major, you can talk about. There are other types of free energy, but this one assumes a constant temperature and pressure. Now, those are useful assumptions for chemists because we can usually control the pressure of our reaction, do it at atmospheric pressure, or the temperature of the reaction, keep it in a hot water bath, or whatever we need to do to keep the temperature constant. But that's those assumptions are built into delta G, and so if that does not work for your system of interest, then you need to find another way. Okay, so we're going to talk over the next series of videos about how to determine delta G, and here we're going to talk about using delta G equals delta H minus T delta S at a specified temperature. So like we said before, a negative delta G means spontaneous in the forward direction. A positive delta G means non-spontaneous in the forward direction, and delta G equals 0 means equilibrium, or we're crossing over at that temperature between spontaneous and not spontaneous. You've noticed that we've dropped the subscripts of system. You can now assume that if it doesn't specify, it's about the system. Okay, so here's our biochemical example. When oxygen binds to the hemoglobin in your blood, we can represent, hemoglobin here is represented as HB. Hemoglobin binds 4 equivalents of oxygen. And for that process, delta H has been measured to be negative 128.8 kilojoules, and delta S is negative 54.7 joules per Kelvin. So what is delta G of the binding of oxygen to hemoglobin at 37 degrees C, which is human biological temperature? Okay, so we're trying to find delta G. And we have delta H, T, and delta S. So there's our equation. Now we can start filling these things in to calculate delta G. So for delta H and delta S, we see that they have different units. Delta H is in kilojoules, delta S is in joules. I'm going to choose to put delta H into joules. But you could very well choose to change delta S to kilojoules. Also, we see that delta S is joules per Kelvin, which means that our temperature needs to be in Kelvin. So we're going to add 273 to convert our temperature to Kelvin. All right, so we fill that in. And if you put that into your calculator, you will get negative 145,757 joules. And so that's a really big number, so we can make that a little bit easier to handle by converting back to kilojoules. And so we get negative 146 kilojoules. So the binding of oxygen to hemoglobin is very thermodynamically favorable. This is a pretty big value of delta G. They're usually in the range of being 0 to maybe 100 kilojoules is a little on the big side. And we see that this is spontaneous in the forward direction. And that's good for you because you want your hemoglobin to transport oxygen throughout your body. So let's talk about how the temperature will affect delta G. And we can think about this by thinking through all the possibilities of the signs for delta H and delta S. So first, if delta H is negative, meaning exothermic, and delta S is positive, which means entropy is increasing, both of those factors favor a spontaneous reaction. And so delta G will be negative and the reaction will be spontaneous no matter what the temperature. If, on the other hand, delta H is positive, so it's endothermic, and delta S is negative, so entropy is decreasing, then that is doubly unfavorable. And that reaction will be non-spontaneous in the forward direction at any temperature. Now, if you take one of the sort of cross relations, for example, if we think about an exothermic reaction where entropy is decreasing, that reaction will be spontaneous sometimes at some temperatures, at any temperature lower than where delta H equals T delta S. So basically what's going on there is that when you, at lower temperatures, that favorable exothermic delta H overcomes the unfavorable entropy because the entropy is dependent on temperature. We can think about the fourth possibility. When delta H is positive, so this is an endothermic reaction, but delta S is positive, so entropy is increasing. That reaction will be spontaneous at higher temperatures, where the favorable entropy can outweigh the unfavorable enthalpy. So let's thinking about hemoglobin again. Let's calculate that temperature where oxygen binding to hemoglobin is not favorable. We see here that delta H is negative, so it's exothermic, but delta S is negative, so entropy is decreasing. Entropy decreasing makes sense. We're going from 5 independent particles to 1 independent particle. So this reaction is going to be spontaneous below the crossover temperature. We can calculate that temperature by setting delta G equals 0, and then putting in our other values, so delta H, and once again, I'm going to convert to joules just because I like that better, but you can do it the other way. We're solving for T, and then delta S is negative 54.7 joules per Kelvin. Okay, if we rearrange that, so we're going to move delta H to the other side and solve for T, we get, oops, I forgot the negative there. So we're going to get 128.8 times 10 to the third joules divided by 54.7 joules per Kelvin. So our answer is going to come out in Kelvin, and I get 2,355 Kelvin. That is a high temperature. That is also 2,082 Celsius. So what that means is that the reaction is spontaneous. Delta G is less than 0 at all temperatures below the 2355 Kelvin. And that's good for you. That means that even if you get a fever, it will still be spontaneous for oxygen to bind to your hemoglobin. We can do a little more conventional example, but we're thinking about going kind of a different quadrant in this case. Here we have a positive endothermic reaction and a positive delta S. Okay, so this is the melting point of water. We're looking at the fusion reaction. So this is solid water or ice becoming liquid water. And so here if we do the same thing, set delta G equals 0, and solve for T. So we get that T equals negative delta H divided by delta S. Then we find that we get negative 6.01 times 10 to the third joules per mole divided by negative 22.00 joules per mole times Kelvin. And so here our answer comes out as 273 Kelvin. And that means 0 Celsius. So we can use the delta H and the delta S to calculate phase change temperatures as well. And so you see here we get the familiar 0 degrees Celsius.